There you go.
Perfect.
Better.
Thank you.
You can introduce yourself, or you want
So yeah, I can introduce.
you want to be introduced?
You are also one of the organizers, so
No,
or I
it's
can
fine.
introduce you.
As you prefer. Here there is a microphone.
I don't care.
Just very quick. So hi everybody. So now with some delay, but not too much, we start the second set of lectures here by Professor Mehrdad Mirbabayi. I hope I'm saying it correctly, from the ICTP, who is an expert on inflation, and he's going to tell us all about how the universe started and how we got the initial conditions for our universe. So thanks a lot for Mehrdad. It's your first visit to Brazil, I think?
Yeah.
Yes. So
Thank you. Thank you. Does this work? Can everyone hear me well? Yes, I assume the answer is yes. Okay, so I'm going to talk about inflation. Thankfully, Raul reviewed many basic things in the previous lecture. I might actually repeat some of the things because I didn't know exactly what he's going to talk about. So some of the stuff that I'm going to talk might have some overlap. But since they are conceptually important, it might be worth repeating them. All right, so the plan is to talk a little bit about Big Bang cosmology, hot Big Bang cosmology, and mention a few problems, serious problems with hot Big Bang cosmology that inflation was originally invented to solve. And then I will explain the simple dynamics, classical dynamics of inflation, give some simple model in which inflation can be realized, and explain how it attempts to solve those problems. Let's see how much of this I can cover today. All right, so I'm going to start from FLRW cosmology. So as we saw, this is the description of a universe which is homogeneous and isotropic. We describe it by a metric, which is called Robertson-Walker metric. A squared sum and spatial part. Let me just write it as d sigma squared. So this sigma, which describes the spatial slices of the universe, it has the property that it is homogeneous and isotropic, and there are actually four possibilities, but I don't talk about the fourth one. So there are three possibilities for this sigma, which correspond to having open, which I denoted by k equals +1, -1. So this, I think we have some different conventions with flat, which is k equals 0, and closed, which corresponds to k equals +1. So this metric is just time independent, whatever sits here. And then we have a scale factor which is time dependent. And in the open case, this has a constant negative curvature. In the flat case, it is flat. In the closed case, this metric, this spatial part is a sphere, so it has positive curvature. Now, if we, another thing is that with the symmetries that we assume, the stress energy tensor takes the following form. It will be diagonal in this coordinate system, And then the diagonal elements, so there will be 0, 0 component, and then the three spatial components have to be equal again because of the assumption of homogeneity and isotropy. And this of diagonal element are going, sorry, these spatial elements are going to call them P, so these are pressure. So I have energy density and the pressure. And then all of the other components of T mu nu are equal to 0. Now, so what do we do? Well, we use the Einstein equations and the conservation of the T mu nu to solve for this model. Einstein equation, which is G mu nu equals 8 pi G Newton times T mu nu. So if we plug this metric ansatz and this T mu nu inside Einstein equations, we get Friedmann equations. The one that I care about is this one. And then we have the conservation of T mu nu, which tells me that rho dot is equal to minus 3h rho plus p. So this system of equations, and I should say that h here is defined as a dot over a, where dot corresponds to d by dt. So a dot is equal to dA by dt. So we have this system, similarly for rho dot. So dot always means d by dt. We have this system of equations we want to, system of ODEs that we want to solve as a function of time. And we can solve them if we know how the momentum, how the pressure depends on density, so which is called the equation of a state. So if we know how P depends on rho, then we can solve this system of equations. Now, we can consider some simple models, which are actually, despite being simple, are very realistic in our universe. To take this pressure to be given by some W to be proportional to rho. With some proportionality constant that we call W. So what are the examples? For instance, we consider matter universe, in which case W is equal to 0. Or we can consider radiation. Actually, I want to do it in the radiation. W equals 1/3. So it has relatively large pressure. Then we have matter. W equals 0. Now, if you look at this equation, there is this contribution that comes from the spatial curvature that we had here. Remember, K is depends on the spatial curvature. So we have this contribution coming from the spatial curvature. We can think of this also as interpreted as some contribution to the rho. And then, as we will see in a second, then K is effectively equivalent to having rho W equals minus 1/3. And then we can have cosmological constant or dark energy, lambda. So that would be a constant rho, and that would correspond to W equals minus 1. So what does it correspond in terms of T mu nu? If you add cosmological constant, then it will add a term on the right-hand side of the Einstein equation, which is proportional to G mu nu, right? So if I have lambda, for instance, there will be lambda times, or there will be a contribution like lambda times g mu nu. And then, therefore, effectively, lambda corresponds to T mu nu, which is just proportional to 1 in this mixed spaces. So it will be lambda, 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 lambda everywhere, which corresponds to P equals minus rho. So W minus 1. OK, so these are some examples which are described, have this form of equation of a state. P is proportional to rho. Now, if we have this simple form of equation of a state, then we can immediately solve for the time dependence of these quantities. In particular, if I look at this equation, energy conservation essentially, what does it tell me? It tells me that rho dot is equal to minus 3h 1 plus w times rho, which tells me that rho is going to be proportional to, so it's given by some constant, let's call it rho 0, times or divided by a to power 1 plus, 3 times 1 plus w. So in particular, if we consider radiation, then let's go here. If we consider radiation, rho goes as 1 over a to the 4th. If we consider matter, then rho goes as 1 over a cube. Here, I exactly chose w equals minus a third, so that I get rho going as 1 over a squared. So that's why we can interpret this as some contribution to the energy density and momentum with this w, because its contribution will be proportional to 1 over a squared. And then if we consider lambda, lambda is constant. Its energy density doesn't dilute with time, doesn't decrease. And here we get just rho constant, just lambda, A independent. So for instance, we can consider a universe that is a mixture of these different components. It has a bit of radiation, a bit of CC, a bit of matter, some curvature. And as time passes, as you see, these components change in different ways. Oh, by the way, one thing that I didn't say, probably you have heard about, is that when I solve these equations, if at some moment it is expanding, then it's well, basically what happens is that this system of equations doesn't want to admit a static solution. So once I consider this model, consider some universe which is homogeneous and isotropic and it's not empty, what it wants to move, it wants to expand or shrink, contract. How can we see it? For instance, let's look at this equation. So this h was a dot over a. So this is h squared is equal to rho. So for instance, if I consider k equals 0 or negative, what this equation tells me is that if we assume that energy density is positive, which seems like a reasonable assumption to make, if you have a universe with positive energy density, then this h squared is given by something positive. So if it starts positive, it just remains positive. It cannot cross 0. So a as a function of time will just continue increasing. On the other hand, if k is positive in here, then there are various possibilities. We can start from expansion, and depending on the composition of these elements that we have, we might continue expanding, or we might have a maximum size for the universe and then go back. So this is something that I'll probably ask you to do in the exercises. You can ask, can we come up with some combination of these components so that the universe is static? And it's actually possible. That's called Einstein's static universe. But you see that Einstein's static universe is actually unstable. So it's like sitting at the tip of this this point. So what happens is that, so let us actually focus on the earlier stages. So imagine we start from expansion. Then what happens is that when you have these various components, then they are going to change with time in different ways. And therefore, you might, so for instance, as we go to earlier times, the scale factor is smaller. And then if these are the only components that we have, at earlier times, the radiation is going to become dominant. Because as A becomes smaller, this part grows faster. That's indeed something that happens in the universe that we observe. As we go back in time, we see that there is an area of radiation domination. As time passes, then if we have some matter, eventually there will be a matter-radiation equality, and then matter takes over. And then you see curvature dilutes even slower, so if there was curvature, it would dominate later, and then we have lambda, which is constant in time. All right, so this is general behavior of these components. They change, the importance changes in time. That's actually a good thing, because then it allows us to do simple approximations. So for instance, talk about the radiation-dominated universe by ignoring all other elements and just solve this equation for a single component, which is very easy. All right, so let us see what happens if we have some radiation. So we want to solve these equations in the case of radiation dominated, because we saw that if we go to early times, then this component is going to dominate. So I can ignore all the other components. I just solve this equation. A dot over A squared is equal to 8 pi g third times some row 0 divided by 8 to the 4. So if we solve this, we are going to get A going as some constant, which doesn't matter much for us, times the square root of t, from which it follows that h is 1 over 2t. In general, for any w, if we have only one single w, we can solve this equation very easily. We get similar behaviors. Actually, let's see if we need it. Maybe we don't need it for general w. Okay, let's first focus on radiation dominated. So what does this tell us? We have the scale factor that goes as the square root of t, and h, the Hubble parameter that goes as 1 over 2t. Now, what this model predicts is that as I go to earlier times, so this is t, and what this model predicts is that as I go to earlier times, the energy density in radiation is going to become larger and larger. Similarly, the expansion parameter is going to become larger and larger. They go as 1 over t, h squared and rho go as 1 over t squared. So as I go to t equal to 0, they diverge, they blow up. And this divergence is called the hot Big Bang. So this is the simple consequence of this model. We consider this FLRW cosmology with these components, then we get a hot Big Bang at the beginning. And this is a true singularity. Energy densities are going to infinite. The universe is very hot. Everyone burns. Of course, so this is called a singularity. At some point at t, presumably of order of the Planck time, then the notion of a space-time and this system doesn't really make sense. So one needs a new description if this is actually what is happening. And this T Planck is defined in terms, is related to this G Newton. I define as 1 over m Planck. And then m Planck is squared, I define as 1 over 8 pi g. Okay, so basically this is the hot Big Bang cosmology. It has a singularity at t equal to 0. Now, what are the problems with hot Big Bang? Hot Big Bang cosmology. One problem with this cosmology, with this model, it can be seen very easily, almost immediately. So let me do the following. Let me define the fraction of different components in this universe. So what we saw was that the fraction of different components are changing with time, meaning that if I take this equation, there are several components in this. So I divide both sides by h squared and get to the following equation. The sum over omega I of t plus omega k is equal to 1. So what is omega? Omega k is just minus k divided by h squared, and omega I is equal to 8 by g, or let me even define another quantity. So omega I is defined for different components as rho I divided by rho critical, and rho critical is 3h squared divided by 8 pi g. So it's the rho that would give us would fully saturate this equation. If I just had that rho, would give me the Hubble. So something defined in terms of the Hubble parameter, Hubble expansion rate. So we get this equation. So nothing non-trivial here. Now, what we saw was that these omegas, they are all functions of time, and they change with time. So these are like fractions, right? These are they are all, at least these omega i's, they are all things that are fractional numbers, so they add up to 1. And in particular, we have this omega k, one of the terms that appear here. Now we can ask, we see that this has this simple dependence on time, and we can ask what is the amount of this omega k today? So as Raul mentioned in the lectures, this omega k in principle is a parameter in our model. We happen to see that this omega k is not that big. In fact, it's relatively small. So if we ask about omega k today, and today, usually quantities today are denoted by a subscript 0. So I say, for instance, omega k at t0, it means omega k today. And this is constrained to be something less than 10 to the minus 2, maybe even smaller. It hasn't been observed. And we have this error boson. Okay, so and we see that this has the following time dependence. So let us ask, what should be the omega k at the initial, say at this Planck time, if we had this Big Bang cosmology? Let us ask what should be omega k at Planck time so that today we get this value. So what do? We compare these ratios. Omega k at Ti is equal to omega k at T naught times A naught H naught divided by AI HI, the square. Right? Now let us also pretend that we are in a radiation-dominated universe, just to make things simple. So let's assume that this A and H, they are evolving with time as we derived it here for a radiation-dominated universe. It's not, in our universe, it's not actually the case. We have at some point we became matter-dominated, and then recently we have become lambda-dominated. But just for simplicity, we can do that. It doesn't really change the, doing it more precisely doesn't really solve the problem. The problem, as you see, is so big that it cannot be solved by just doing this little change. So if I just do it in radiation domination, then I get omega k, and for Ti, I want to put T Planck. Now, what about this ratio? In radiation dominance, H goes as 1 over T, and A goes as the square root of T. So this ratio is just is T Planck divided by T0. Now, what are these numbers? I guess you can already see that we are going to get something really, really small. So what is T Planck? T Planck is something I've ordered, so I forgot to say here. This M Planck that I define in terms of G Newton is a constant of nature. M Planck is something over the 10 to the 18 or 19 giga electron volt. And then it means that T Planck is something over the 10 to the minus 43 seconds. And T0 is over the 13 billion years, which means that it is over the, so it is 13 times 10 to the 9 years. And this thing is something over the 10 to the 7 seconds. Sorry, 17. Thank you. So what is the ratio? The ratio is, so what we get is that omega k at T Planck, since we have omega k at T0 to be less than 10 to the minus 2, we get omega k at T Planck has to be less than 10 to the minus 62. And so that is something that is called the curvature problem of the hot Big Bang cosmology. The curvature problem is that whatever initial condition that we had, so imagine we had this hot Big Bang. We emerged from this Planckian regime about which we don't know much, with some initial condition. Now, this initial condition should be extremely precise to this order, so that the curvature that we measure today is less than 10 to the minus 2. And so this amount of precision is a little bit troubling. So we want to find a way to solve this problem. And inflation is a mechanism that solves this curvature problem because it makes curvature extremely small by having an error of nearly error of accelerated expansion, an error in which we are nearly lambda dominated. Okay, there was a question there. No? Okay. Is there any question anywhere else? Yeah?
So to arrive in this conclusion, you have to rely on the fact that you can describe all these fluids by perfect fluids throughout the whole history of the universe, right?
Uh-huh.
And also you assume that this equation of state is always the same. Because I'm just asking because if you have a very dense universe, for instance, couldn't you have corrections to this equation of state so that when you go to the Planck scale, then the solution is not this one?
Okay, thanks for the question. Actually, I didn't make an assumption that the universe is made of perfect fluid, because this form of the stress energy tensor is just dictated by the symmetry of the universe. So whether this fluid or whatever matter that we have in the universe, whether it is a perfect fluid or a dissipative fluid, doesn't matter. It's T mu nu. If we have these symmetries, if we have homogeneous and isotropic universe, we'll have this form. Now, therefore, the question that remains is the assumption about W. Why did I assume that W is 1/3 all the way? Now, I didn't have to. In fact, in reality, it's not 1/3 all the way. It's 1/3 at the beginning, and then it changes to something else. The point is that as long as W is something that is not what I'm going to call inflation, this problem is going to be there. And in fact, inflation is basically changing that situation but at earlier times by going into a different phase in which you have a different expansion law compared to radiation dominant. So it's natural to assume that if you have a hot Big Bang, you should be radiation dominated. Everything, if you make anything too hot, it becomes like radiation. So the solution to the problem is to have a cold phase, which is called inflation, before that hot Big Bang.
The x-axis in that plot. I didn't understand.
Where is what?
That plot over there, the graphic, the axis. Where is the vertical axis time, but the horizontal?
Oh, this is just x. This is supposed to be a space-time diagram. I think he has another question. All right, follow.
It's just because I wasn't thinking on changing W, but actually in something more complicated, because let's assume, for instance, you have a gas, and in some regime you can describe it by an ideal gas, but if you take into account that particles and molecules have a size, you have to describe the equation of state, for instance, by van der Waals gas. And my question is maybe not only the equation of state, the equation parameter of the equation of state W is different, but also it's more complicated. So you have like a virial expansion of this equation of state in that regime.
What kind of expansion again?
Like P as a power law, not as a power law anymore, actually linear, but actually you have some constant times rho plus another constant times rho to some power, and then you have a new dynamics to your continuity equation, and maybe somehow this kind of conclusion is not achieved.
Yeah, but it's true that was a very simple model for the pressure, for the equation of a state. Maybe one other way of phrasing the problem is that, well, you can probably play with different equations of a state. There are two qualitatively different regimes that you can imagine, right? The two qualitatively different regimes are the ones in which this factor, a squared h squared, we are going to see it in also different, in a different situation. One is in which this a squared h squared is growing with time, or let me write. So let's look at this quantity a times h. Right? What is it? This is h a dot, right? So we can consider two scenarios. Either a double dot, which is time derivative of this, is larger than 0, and a double dot is less than 0. Well, of course, it can be also 0, but that would be called that would be the theta constant. So there are these two possibilities, and this is the one that we get in these simple scenarios: a decelerated expansion. Now, the point is, as long as you have decelerated expansion, then what happens is that you are going to encounter an initial singularity unless we go to another phase of accelerated expansion, or to get a bounce. Unless we have that, then this quantity will decrease in time. And when this quantity decreases in time, what happens is that omega k at initial time has to be much, much smaller compared to the omega k today. So if we measure it to be 10 to the minus 2 at initial time, it has to be incredibly small. So essentially, that complicated equation of a state that you imagine that changes this behavior is basically what I would call inflation. It's the period that gives you accelerated expansion that makes this parameter grow in time instead of decrease in time. Okay, so this was the curvature problem. Okay, let me now talk about the conformal time. Again, Raoul mentioned this conformal time in his lecture, so I'm repeating what he said. So why am I going to introduce conformal time? So there is this form of metric. This t that is here is a physical time. Why is it a physical time? Because here I can consider a geodesy, a co-moving observer who is just sitting there. And this t is the time that his clock is measuring. So it's a physical quantity. Now I'm going to define the conformal time in the following way. I take dt to be a times d eta. So conformal time is eta. And then the form of the metric becomes a squared times minus d eta squared plus the spatial part. Now let us also focus on k equals 0 for simplicity. Then this becomes just dx squared if we assume k is equal to 0. Now, why is it called conformal? Because the metric is not conformally flat. This is just a flat Minkowski metric. And the good thing about this coordinates is that if I draw this diagram that I had here, if I draw it in terms of eta instead of t, then when I'm working with conformal coordinates, then in these coordinates, the null geodesics or lights, they will travel at 45 degrees, so they won't be modified by this change in the conformal factor. So in this plot, I can draw 45-degree lines, and they determine the propagation of the light or null signals. Therefore, for instance, I can talk about the path light cone of an observer who lives in this cosmology. So let us talk about that. We want to see, we have an observer in this cosmology like us. And we are looking at the universe. Of course, the only thing that we can see is within or past light cone. So we want to see how far we can see, how much of this, say we are in this Big Bang cosmology, how much of this cosmology can we see in our past? How do we do that? So in this coordinates, everything is extremely simple because the distances and times are the same. The distances and times that are traveled by light are the same. So if I want to determine this delta x, which you were calling it co-moving distance. Co-moving radius. So if I want to measure co-moving radius, I can instead calculate the conformal time. Conformal time up to this slice is the same as the co-moving radius up to which I can see. So how do I calculate the conformal time? It's easy. It's just integrate dt over a. And in general, for general W, as long as it is larger than 1/3, I'm going to get 1 plus W times HA. And I'm assuming that I'm calculating it, say, from 0 up to sometime t. So this W, again, is some order 1 number. So the main thing is that this co-moving radius, or the conformal time up to essentially the size of the region that we can see goes as 1 over HA. And this 1 over HA, as we calculated here for a radiation-dominated universe, or for anything that for which W So again, I should say here that W is larger than minus a third. And the time dependence of this delta eta, which is, by the way, so let's define delta x. Delta x is the co-moving distance up to which we can see. So what experiment are we considering? We are considering observers, and then they are looking at their path, and now we are measuring this distance. So this is delta x1, this is delta x2, and so on. And that delta x is the same as this delta eta that I calculated here, and it's given by this quantity. It's something that is proportional to 1 over HA. And therefore, as a function of time, when W is larger than minus a third, this 1 over HA is growing with time. So as time passes, we see more and more. And now we encountered the second problem of the Big Bang, hot Big Bang cosmology, which is that now here it's very easy to see. I didn't even need to say much about these things, because as I mentioned, in conformal time, I can just draw pictures. And the pictures do not lie to us in this case. So I can see all of this. We are sitting here. This is T0 or eta 0. And then we have a recombination surface. The recombination surface in this diagram is sometime between us and the initial singularity, if there was such a thing. It's actually, if we calculate it, it's very close to this t equal to 0 line. So let's draw it here. So this is the recombination surface. This is the surface from which the photons, the CMB photons, traveled almost freely until they reach us. Now, when we look at this recombination, or the CMB photons which come from the recombination surface, we see that they are incredibly homogeneous. The temperature on this surface, it has very small fluctuations, but it's homogeneous to very good accuracy. Now let us consider different points on this recombination surface and see how much could they see in their path. So again, this plot, we can just draw things. So these are the light cones of the points on the recombination surface. By the way, this path light cone, or this distance that we can see until t equals 0, is called particle horizon. This is an important concept. So this is particle horizon. The word horizon is going to appear in my lectures many different times, many different meanings, although they are always kind of related to each other. But maybe at the beginning it might be a bit confusing. Anyway, this is called the particle horizon. And so when we look at our particle horizon, it's much bigger compared to the particle horizons of different points at the recombination surface. So then the mystery is that how could these different points who never had causal contact with each other, never saw anything, what they saw in their past has nothing in common with each other, how come they got so incredibly homogeneous or uniform? So this is, again, another sort of fine-tuning of the initial condition. We have to have initial condition which is very homogeneous over regions that are not causally connected to each other. Now, how does inflation solve this problem? So this is, by the way, it's called horizon problem. The way inflation solves this problem for us is that it removes the initial singularity, or the hot Big Bang singularity, and introduces a new phase in the past of this hot phase. So we have the hot phase, and then we will have the inflation phase. And what happens in the inflation phase is that these different points, faraway points on the recombination surface, which were not in causal contact with each other, during inflation they come in causal contact. And then afterwards it won't be surprising if they are very homogeneous, because they had seen each other before. They have received information from some small region which was in causal contact with itself. So they could be then become homogeneous and uniform, and then we will see that they actually become homogeneous and uniform. All right, so this is the second problem with hot Big Bang, how inflation tries to solve it. Is there any question at this point?
So that's still something that is strange for me in the horizon problem. So it seems that it appears only if you observe the last scattering at late times. Or, for example, if we measure it 5 billion years from now, we need more inflation to solve it.
That's a good question. Let me think a bit. So okay, let us consider a simpler case, because now it's a bit hard for me to answer if we are in the lambda-dominated universe. The answer might change in the lambda-dominated universe, but if we were just say matter domination or radiation domination, then what would happen is that yes, this size would keep growing as we go to later times. And then we would need more and more inflation to explain the homogeneity of the universe over those larger scales. So the answer is yes, at least if we are not, if we are in lambda dominated, then I'm not sure if we are going to get access to much more, because we have another horizon to deal with.
And also, if we measured the last scattering right after the last scattering, not so time later, we will not find the horizon problem. I think.
No, I mean if you can. Light after light is right after recombination means what? Means that basically you don't see anything. You are like, imagine if we couldn't see the CMB, we couldn't even come up with this problem that there are two faraway points which look similar. Or you need to. I mean, the problem is really that you are seeing regions that have never been in causal contact with each other. Then you can talk about horizon problem, because you can ask how come those regions who were not in causal contact, they happen to be so similar. If they have been in causal contact, you can imagine a mechanism that allows inhomogeneities to dissipate, and then you uniformize things. Other questions? So let me just reiterate this point here. Maybe just repeat it there. So you see that again we are dealing with the same quantity that determines this particle horizon. And the problem, we had this problem, or this horizon problem, exactly because this quantity, this horizon, this particle horizon was growing with time, which means that HA was decreasing in time in this model, this cosmological model with W larger than minus a third. So these problems arise when we have this decelerated expansion. And the way inflation solves both of these problems is to give us a period of accelerated expansion. During accelerated expansion, this horizon it becomes, in this case, it was dominated by late time. So if you age longer and longer, you see bigger and bigger sizes. The problem becomes more severe. While if you go in the accelerated expansion, this particle horizon becomes dominated by the early contribution. So it doesn't matter how much longer you stay. And similarly, this curvature that was omega k that was growing in time during decelerated phase. During accelerated phase, it decreases in time. So if you have long enough inflation, you can start from omega k of order 1, decrease it in time, and then so that it becomes small enough that the amount of growth from end of inflation until today, we just bring it back to some order 1 value, or maybe order percent value. So it's just enough to have enough deceleration here. Now since we are here, we can also imagine another possibility that sometimes people discuss, because I'm not going to talk about it later. That's the subject of alternatives to inflation. So alternatives to inflation, as the name implies, they are alternative solutions to these problems. And since they have to be solutions to this problem, they have to actually give us this positive A double dot. So how do we achieve this positive A double dot? Let me just look at it here. If I take the derivative of this A dot, what do I get? I get H dot. I'm canceling a factor of A. I get H dot plus H squared. And we want this to be larger than 0 to solve these problems. Now, there are two options. Option number 1 is that H dot is negative, and therefore we want minus H dot to be less than H squared. This is what I call inflation. And we are going to talk a lot about it. Option number 2 is when H dot is positive, H dot is larger than 0. And this is not inflation. However, there are alternatives to inflation which have satisfy this property. For instance, one of them is called ekpyrotic universe. And they achieve the same outcome, which is that they basically solve these two problems. However, having h dot larger than 0, it requires violation of some condition on energy momentum tensor, which is called null energy condition. So I have to violate this null energy condition. In short, it's called a NEC. And there are some issues with this null energy violation of null energy conditions. First of all, because we don't have any reasonable model, any model of fundamental physics that violates null energy condition in a way that we can get these solutions, these cosmological solutions. There are even some more or less formal proofs in quantum field theory that null energy conditions, some versions of null energy condition have to be satisfied by proofs based on axioms of quantum field theory. Now, I should say that the versions that have to be satisfied are called the average null energy condition. There is violation of null energy condition in some theories, quantum theories. For instance, if you consider Casimir effect, that can violate null energy condition. But those violations are called safe violation of null energy condition, in the sense that they cannot be used to get this kind of bouncing cosmology. So for instance, this cosmology with h dot larger than 0 can allow you to have a contracting phase, and then from a contracting phase, you bounce back into an expanding phase without going through a singularity. The violations that we know in quantum mechanics, they are usually very mild. They don't allow us to do such a thing. The ones that allow us to do such things, we don't know how to give a fundamental description for them. So there are issues with these scenarios. That's at least one of the reasons why inflation is much more popular. It's harder to come up with alternative models. Okay, so that was what I wanted to say about the alternatives. I guess now I can just talk about some model of inflation or explain how inflation solves this problem. Is there any questions so far? No. All right, so how does it solve? Yeah, as I mentioned, we want a double dot to be negative. So let me give you, from the beginning, let me give you some very simple model. Having a double dot less than 0 doesn't necessarily mean that we are in the seater. Oh, by the way, I didn't say what the seater is. So, but now I'm going to say. So I want to consider inflation to be some phase of nearly the seater. And what the seater is that if you imagine, so let's first talk about the seater. If we had this, if we consider this for double cosmology, but only with lambda and nothing else in it. So if we only had lambda, then that would give us a solution which is minus dt squared plus e to the 2ht times dx squared. Where here h is just a constant. related to the cosmological constant. So h squared is a constant which is given by 8 pi g lambda divided by 3. Maybe I put an I here. So this is H inflation. Well, inflation is supposed to be, so how did I get this? I got this solution by just adding a cosmological constant to the Einstein equations. Now the zeta is, the inflation is not exactly the zeta, but it has in common the property that it gives us accelerated expansion. And it gives us accelerated expansion for a relatively long time, as we see now. And having that for a relatively long time, it means that it has to be relatively close to the zeta. So we will see better, we will quantify this closeness to the zeta better in the future. We have data and observations that tell us how close we have to be to the zeta during inflation. And close to the zeta in particular means that the Hubble scale is how constant it is, how small is the variations of the Hubble parameter. All right, so this is called this is the zeta metric in some particular coordinates. This is called the cosmological coordinates of the zeta, or the cosmological patch of the zeta space. The zeta space is a bigger space, and you can cut it, or a bigger manifold that you can cut it in some particular way and get this cosmological solution from. All right, so now, and so this is what we got from lambda, which is W equals -1. So what inflation, the property of inflation is that it has W equals -1 plus some small correction, where this delta is much less than 1. Now what we can do is that we can calculate this quantity, for instance, eta, or this particle horizon during inflation, or the change of eta, which, as we saw, it tells us how much distance we can see. So this delta eta from some Ti to Tf, dt over A, if we are approximately the zeta is given by Ti to Tf dt e to the minus ht, and this is hi. So I get 1 over hi times e to the minus hti minus e to the minus htf, which I can write as 1 over hi ai times 1 minus e to the minus h times tf minus ti. So this quantity h times tf minus ti is called NE, the number of E foldings, because what happens is that the size of the universe changes by E to the n during this period. So this Ti and Tf are supposed to be the initial time and the final time of the inflation, and the amount during which the universe expands, or the scale factor grows during this time, is e to the ne. You see that the distances expand in this inflation phase or near the CTF phase, they expand exponentially fast. And that's exactly what allows us to solve this problem. These regions that were out of causal contact from each other during inflation, what happens is that they are actually start from some little region which was in causal contact, and then it expands so fast to very large distances, superhorizon distances, which are now, which are during this time out of causal contact. So that's what this exponentially expanding phase does for us. Okay, so the question is, the quantitative question to ask is that how many e-foldings of inflation we need to solve the problems that we were dealing with. And here we can determine that that's going to be about 60 e-foldings. So how do we determine that? We want to, let's look at the curvature problem. So the curvature problem was, we wanted to look at the ratio of the omega k at two different times. And that was very easy, right? Omega k at ti divided by omega k at t naught. Let's say we want this ratio to become order 1, for instance. Right, so we start from some order 1 omega k, and also today we see order 1. Well, we see that omega k has to be less than 1%. So what is this ratio? So omega k goes as 1 over AH squared. So this ratio is A0, H0 divided by AI, HI squared. Now, let me write this as in the following way. I write it as A0, H0 divided by AF, HF. So F, remember, was the end of inflation. But the expansion rate does not change much during inflation. So HF and HI are relatively close to each other. They don't differ much. So here I have HF, but I replace it with HI. And then the rest would be AF divided by AI squared. Okay, now what is this ratio? This ratio depends a little bit on what happens at the end of inflation, right? But again, for simplicity, we can assume that at the end of inflation, we immediately go into a hot phase. That's called reheating. Reheating is a mechanism or the period at which inflation ends and the energy density in the inflaton, which is the field that derives inflation, that energy density is converted into heat, into a standard energy in the standard model. So that there are different models of reheating, and it can happen in different ways. But the simplest situation to consider is that when inflation ends, we immediately reheat and get a hot phase. So we immediately go into radiation dominance. And then I'm also going to approximate everything else until today by radiation dominance formula. If you use the fact that it's not exactly that, wouldn't change this estimate, as we will see why. So first of all, I already made an approximation by replacing HF by HI. And now I'm going to make another approximation to say that here I estimate this quantity in the radiation-dominated phase. So then this ratio is T, or, okay, let's remember something from here. So here we did that estimate in radiation dominance. We were looking at this ratio. Now this ratio is in radiation dominated, A times H, it goes as square root of T. But square root of T is just 1 over square root of H. So this ratio, if I want to calculate in RD, or let me do this. In RD, this ratio is just given by H0 divided by HI. Because H goes as 1 over T, A goes as a square root of T, therefore H goes as 1 over square root of T. I square it becomes 1 over T. 1 over T is H. So this is, in radiation domination, is approximately that. In other phases, it's slightly different, but wouldn't change our estimate by much. So I get H naught over HI. And here I get e to the 2NE by definition of the number of E foldings. And then we want to evaluate this, or we want this to be of order 1, which tells us that e to the NE, we want it to be of order of HI over H0. Now, as we later see, so this HI is the Hubble, the expansion rate during inflation. That can have different values. But the data will put some constraints on it. For instance, we know that this HI has to be somewhat less than 10 to the minus 5 times M Planck. And H naught, that we already determined here, right? This ratio, H naught compared to M Planck is basically this ratio of T Planck over T naught, which was 10 to the minus 60. So this H naught is approximately 10 to the 60, 10 to the minus 60 times M Planck. Okay, so if we combine this together, we get NE should be of the order of 60. Maybe 62. So if you have about 60 E foldings of inflation, then we can solve this curvature problem. Now, okay, another something important I have to emphasize here is that this NE was what? Was log of HI over H0 that I said it has to be of order 60. Now, I made many approximations here, right, and many assumptions about how reheating happens, how the transition from inflation to the next phase is going to be fast or slow. The important point to realize is that this formula is relatively insensitive to those assumptions. For instance, the scalar inflation. It's because NE sits in the exponent. So we are only logarithmically sensitive to those details. So this estimate of about 60 E-folds of inflation is relatively robust. It's not going to change much. Maybe it becomes 55, for instance, if you change the details. But it's not going to become 10 E-folds or become 150 E-folds because of those E-folds. All right, so yeah, I guess I have convinced you, hopefully, that this exponential expansion solves the curvature problem, and also solves the horizon problem, because basically both of those are talking about the same quantity. So the moment I satisfy that condition, I have also guaranteed that the particle horizon of the points in CMB are going to intersect with, the points on two sides of CMB are going to intersect with each other, because the particle horizon is determined by the same combination 1/h. So at the same time, I have solved both of the problems by this requirement. So now I have what, like 10 minutes, 7 minutes? 7, okay. Let's see what I can say in 7 minutes, or maybe you can just ask questions if you have. Okay, if you don't have, if you don't have questions, then maybe I just give an introduction to a slow roll inflation, and then we continue in the afternoon. So how do we realize inflation? It's actually very easy to get a model of inflation. We just need a scalar field with a potential. So as Raoul mentioned, one of the examples, if we consider just a scalar field with normal kinetic term and a potential, then we can calculate T mu nu for this. That is left as an exercise. But in particular, if you look at the case in which I have a uniform solution, homogeneous solution, so phi is just phi of t, then, of course, in general, that T mu nu should take the form of the T mu nu that I wrote there, just by general symmetry argument. Now, in this particular case, that rho is going to be 1/2 phi dot squared plus v of phi, and p is going to be plus 1/2 phi dot squared minus v of phi. Right? So now, if we want W to be close to -1, you see that the potential itself satisfies it. So if we just had the potential, it would be W exactly equal to -1. What does it mean? It means that if you just had a scalar field, phi, if it had a potential which was just flat, of course that is the same thing as CC, right? A flat potential, I might as well call it lambda because it doesn't depend on phi. So a flat potential is just lambda, and of course it gives me a cosmological constant in the Einstein equation, or it will give me the T mu nu that is equivalent to the cosmological constant. Now, we don't want inflation to be exactly de Sitter. In other words, we don't want this T mu nu to be exactly that of CC, because we want inflation to end or the phase of the universe to start. So this cannot be like this. So the idea is to tilt it a bit. And then the inflaton rolls down. And eventually, when the potential is low enough, we will enter a new phase. We have reheating and enter the new phase. So this is called a slow roll inflation. whose dynamic we are going to discuss in the afternoon.
Can you consider coupling between gravity and the inflaton in the action?
The coupling between gravity and inflaton in the action. Oh, well, when I write this, I am kind of implicit about those coupling. Of course, this is minimally coupled to gravity. So if you want to be more explicit, there will be an action here. And that, of course, depends on, so S of phi will, of course, depends on the metric. So there will be d4x square root of minus g times minus g mu nu, no, minus 1 over 2 g mu nu d mu phi d nu phi minus v of phi. I don't know, is this what you were asking? Okay. Yeah, it is definitely coupled to gravity. There's no choice about that.
And you also have to include bridge scalar in the action, right?
Sure, yes. This is S of phi, and then there will be also the action for the gravitational part of the action, which we take to be just the Einstein-Hilbert action. So this is S Einstein-Hilbert, and that is given by square root of minus g times r up to some boundary terms. And yes, so if we take the full action to be S gravitational plus S phi, and then vary this action, it leads to the Einstein equations. And it will also give us the equation of motion for phi.
Oh, sorry. Yeah. So, no more questions. Well, Mehrdad is going to give a second lecture this afternoon, so we are exploiting him a lot today. So there will be more opportunities to ask questions. So I couldn't stress it enough. We should all be asking questions a lot, any kind of questions, and let's see if we get this, get these questions out of you as soon as possible today, later. All right. So please don't refrain from asking questions. Now for lunch, do you want to give some? Yes. So just Antonino here, who knows the region better, will tell you something about it. But for those who are not from around here, try to couple, there are many places to eat around here, but try to couple with some of the Brazilians so that you know the system. We have a very particular system for having lunch here, so if you couple with some Brazilians, they will let you know basically the mechanics here. There's a buffet, you help yourself to anything you want, and then they weight that thing in the end. So that's it. It's as simple as that. So just... now Antonino has some tips here.
So in the folder you received, there are 5 tips for lunch. The first, more or less all of them are buffet per kilo. So you pay how much you get. And the first 2, Mossa Prendata and Mirandella, are on the same street, and they are typically Brazilian. Tanta Felicità is Italian. Then we have Japanese, And there are also places that are not here. They are in the street back to the institute, in which you can eat a full plate with only 10 reais.
Wow. Yeah, if your budget limit, yeah, there are options that if you are budget limited, with $3 you can eat a substantial meal.
Yes.
And you can also pick and choose. So, yeah, talk to me if you are budget constrained. Yeah.
Okay, no, we will meet here again at 2. Okay. Have a good lunch. Please take your belongings with you because this room will be open all the afternoon. So.